So now we can kind of get an idea of what these 4 molecular modes of motion look like and what kind of populations that they have. And so I'm going to talk specifically at 298K now, and still more generally like a general molecule. But as we can see, this is true for almost all molecules at room temperature. At 298K, this is the critical piece here. Okay, so we expect at room temperature, all molecules, all of them, will be in the ground electronic state. There's just not enough thermal energy at 298K to populate upper lying electronic states. There's just not, and we're going to calculate that soon. As it turns out, even with the vibrations, 99.9999999% will be in the ground vibrational level. So perhaps a very, very small fraction will be in the vibrational level. Even so, we expect at 298K, all molecules will be in their ground vibrational state. Now, as it turns out, there's a distribution in the rotational levels. And that's because the levels are very finely packed together. So that was one of those postulates, right? The finer the levels are together, the closer they are together, the more of the upper lying states will be populated. So what we will actually see is an actual distribution. Hopefully these little scribbles I'm doing make sense. If I scribble all the way over, that means the level is completely populated. So the rotational levels will actually have like some kind of distribution where there will be some peak energy level, maybe 1, 2, 3, 4. Perhaps the 4th level of the rotations will be the most populated level. Okay. And then with the translations, we also expect some type of distribution, right, where there is going to be some maximum populated state, which would correspond to like the most probable speed that the molecule's traveling. And we're gonna take these kind of sloppy diagrams that I'm making and turn these into actual graphs of the distribution of populations of states. Okay. And so now this gets us to the equipartition theorem. And this is another set of conceptual information I want you to know. And the equipartition theorem says, in a sample of temperature T, all quadratic contributions to the total energy have the same mean value, which is 1/2 times the quantity K Boltzmann times the temperature of the system. Okay, so I'll say this again. In a sample of temperature T, whatever the temperature is, T for the generic temperature, all quadratic contributions, so, right, something raised to the square. Whatever that parameter is, we'll see what that parameter, that quadratic is. All quadratic contributions to the total energy have the same mean value, which is 1/2 times Boltzmann's constant times temperature. Okay, this is a rather obscure theorem, but we're going to prove in several different ways this week and next that this theorem is a damn good one.